Multi-layer conduction is pretty common in industry because if you have a pipe that is above room temperature, you're going to want to put a layer of insulation around that pipe so that you don't have so much heat loss. As soon as you add another layer of material to that pipe that is not like the original material, so for example, insulation and then metal, you have multi-layer conduction. In the first multi-layer conduction video, we looked at multi-layer conduction through a flat wall. Let's take a look at what it looks like through a cylinder because that gets more complicated. The radii are changing as you move from the inside of the pipe to the outside, so the equation to solve these problems looks a little bit different. Here's an example problem. This problem is a modified version of the original problem we saw for conductive heat transfer through a pipe. This time, we're asked to find the rate of heat transfer from the inner pipe wall to the outside of the insulation layer. So we're going through both the metal pipe and the insulation layer. Let's draw a diagram of what this looks like. Okay, here we have our inner pipe and we have our outer insulation. We have three radii that we are concerned with. The first is the very center of our inner pipe to the inside wall of the pipe. The second is the center to the outside wall of our pipe, and the third is the center to the outside surface of our insulation. We're worried about all three radii because we are worried about the heat transfer from the inner pipe wall all the way to the outside edge of our insulation. So let's take a look at what that equation is like. Okay, we have two layers in our overall cylinder. One is the pipe layer, the other one is the insulation layer. So let's indicate those. Notice how we have our radii arranged. The larger radii over the smaller radii. The reason we do it that way is because we want that term in our natural log to be positive. So bigger number over smaller number in a natural log always gives you a positive number. Same thing for the insulation, bigger number over smaller number. We're using R2 and R1 for our pipe because those are the inner and outer radii of our pipe. We're using R3 and R2 in our insulation because R3 is our outer insulation radius, R2 is our inner insulation radius. And yes, the outer radius of the pipe is the inner radius of the insulation. The insulation is wrapped right around that pipe. So where the pipe stops, the insulation starts. Therefore, you're going to use R2 in both the pipe and insulation terms in your denominator. The numerator for your equation looks pretty much like it did for a single layer conductive heat transfer for a pipe. The only difference is now your thermal conductivities are down in the denominators because you have to assign the proper thermal conductivity to the proper layer. That's why they show up down there instead of in the numerator. We're all set to solve for the rate of heat transfer, or Q, and our equation is set up so that we can solve for Q directly. So let's plug all our numbers in and figure out what Q is. Okay, Q is 14.6 kilowatts. If you remember the original answer to this problem, where we looked at heat transfer through the pipe with no insulation, that was about 18.7 kilowatts. So 14.6 versus 18.7 may not sound like a huge difference, but this really does add up over time. Think about a watt as a joule per second. So every second, 14.6 kilojoules of heat are escaping from this pipe versus 18.7 from an uninsulated pipe. Now multiply that by 60 to get the heat loss per minute, by another 60 to get the heat loss per hour, and by 24 to get the heat loss per day. If you do that for both of those numbers and you subtract the insulated pipe number from the uninsulated pipe number, that makes a pretty big difference in how much heat you're losing per day. So yes, we only dropped the heat loss by a little bit, but it's still enough to really make a difference over time. Let's take a look at these radii in this term, the insulation term. It's pretty easy to see where the 0.125 and the 0.0065 come from. Those are given to you in the problem as the outside and inside diameter of the pipe. The 0.0195 radii came from the outer radii, which is 0.0125 for the pipe, plus that insulation thickness. So when you add 0.007 to 0.0125, you get 0.0195, which is the outer radius of the insulation. That's where your third radii comes from. So remember, when you're given a certain thickness of insulation, that is part of the radius. So don't forget about the insulation thickness when you're trying to figure out what's the radii of my insulation. Just like in the flat wall equation, if you had a third layer in this pipe, let's say you had another layer of insulation because you wanted to get the heat transfer down even further, you would just add a third term in this denominator, and that would be the natural log of R4 divided by R3, all of that divided by your third thermal conductivity. And you could just keep stacking on terms like that for as many layers on this pipe as you wanted. One thing we didn't account for in this problem is what's going on between the fluid in the pipe and the pipe wall. That's convection. And so if we want to think about convection and conduction together, we need a new equation. And in another video, we'll take a look at that equation and see what happens when you have several different modes of heat transfer occurring in the same scenario.